Okay, so here's the problem we're interested in. We want to find an explicit matrix A. It's an n by n matrix over some field such that, let me first say it in words, such that you cannot factor or decompose A or two sparse matrices. So let's write it like whenever A equals B times C, the sparsity of B plus the sparsity of C is large. Sparsity is just number of non-zero entries. So let me just use this notation. Large. We will say in a second what we want, what is large. You also ask the most, slightly more general question about factorizing into product of D matrices. So A equals A1, A2, dot, 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 AD. And now we want the sum of the sparsities to be large. So a few comments. I guess I don't need to say it here. Explicit means that we actually, of course, want a family of matrices, one for every n, and we want to output the nth matrix in polynomial in time, which is polynomial in n. It really makes sense over any field, but for this talk, it will be helpful to think about. It's not good to write there, right? But think about f, for example, being complex number or large. So B and C, like what are the dimensions? It's not, I mean, it's not a ton of, I mean, okay, so A is a square matrix. It doesn't have to be square. I mean, ask it about rectangular matrices, but it's helpful to carry one less parameter around. B and C don't have to be square. So like this would be n by m, and this would be m by n. And here, okay, I want it, but whatever it needs to be for the multiplication to make sense. Okay, so this is a problem. Let me tell you why you should care about it. So it's a long answer that I will spend some time on. But just like the table of contents of the answer. So the first reason is, okay, this algebraic complexity, which is why we're here for. And I will also mention some matrix rigidity, which is, okay, I will define it. And then, okay, I will see how it goes with the time, but I might say some words on lower bound for data structures. And then there's this other thing, I'm not sure how many people have heard about it. It's this small field called machine learning. So where I come from, it's a little bit bigger than algebraic complexity. I think in India it's comparable sizes, but so here I really don't know anything, but I will still say a few words because you cannot have a week-long conference without saying the word machine learning nowadays. Okay, so let's start with algebraic complexity. Okay, so you know we want to compute polynomials, and we have algebraic circuits, and then compute polynomials, and that's nice. The simplest class of polynomials, I think, well, there are the zero polynomial, but the next simplest is linear polynomials, right? So we want to consider circuits that compute linear functions. So you have a vector x. So x is a vector. It's like x1 to xn. And you want to compute A times x as the linear transformation. A is an n by n matrix. And the question is, how well can you do it? Well, one good news is that it turns out that if you compute linear transformation, you don't need multiplication or division. You can just do operation, and this model is called a linear circuit. So it will be a definition by a picture. Oh. Now it's thicker. So a linear circuit is just this thing that you start with the inputs. Let's say these are x1, xn. And now each node computes a linear function of its children. So there are those edges, and the edges are labeled by field elements. So this one, you don't want to draw the labels because it's useless, but just a combination of the inputs and so on. And then you continue like this. And let's say this is the output level. So again, you take linear combination. Okay. So that's a linear circuit. And again, you can convert any arithmetic circuit for linear transformation to a linear circuit. And you only lose a constant factor, so that's generally enough. Okay, several things. So here I do it in like a depth 2 thing. It can be, of course, in larger depth. I also do it layered in the sense that every edge goes either from this layer to this layer or from this layer to this layer. It doesn't have to be the case, but we can, at least when the depth is constant, we can assume it is the case. Because if you have this edge going like this, I can just break it up in 2 and add some another dummy node here. The number of edges goes by at most a factor of 2. This is still fine. Now you look at those things, and you look at this thing, and it's some graph, and the adjacency matrix of this graph, you call it C. So this layer computes the transformation Cx, and then you call this layer B. So this computes B times C, the composition of B with C. So just a small depth 2 circuit just means that A equals BC, and the sparsity measures the number of edges in this graph, right? So to say A can be factored as 2 sparse matrices is exactly the same as saying that A has a small depth 2 linear circuit. It's really direct translation, and you can do the same thing for product of D and depth D. It's the same question. So yeah, so we want to prove lower bounds on such things. So there are good news and bad news. And the good news is that we can prove superlinear lower bounds on such circuits when the depth is constant. But they are very weak lower bounds. So let me first describe how you prove it. So one thing you can do, which is a useful observation, I think it goes back to Valiant. Let's say we fix some subset of the input and some subset of the output, and they both have size k. So this corresponds to, when we just look at the subgraph, it computes like this matrix. And so this has k, and let's say k, and let's assume the rank here is k. This is a full rank submatrix. So the only observation is that whatever let's look at the subgraph here, whatever the minimal cut in the subgraph is, it has to be at least k, right? Because if it was k minus 1, you would factor this matrix as a sum of k times k minus 1 and k minus 1 times k, so its rank cannot be k. So, but this is, okay, so it seems our best bet would be to take a matrix that all these minors are non-singular, right? It's easy to construct, again, over large, such explicit matrices that whenever you look at minors of all orders, they are non-zero. And the corresponding graph thing is that whenever you look at subset of the input and subset of the output of any size, let's say call this size k, the minimal cut has to be of size at least k. And intuitively, it seems that such graphs need to be large. Okay, this graph has a name, by the way. They have a name. They're called super concentrators. Takes a long time to write. And what I said, true, okay, for depth 2, minimal cut is just number of common neighbors. For larger depth, it's, well, it's minimal cut. So graphs that have this property are called superconcentrators, and there are such graphs of linear size, but in constant depth, we can prove. So let me just quote this theorem, that any depth d superconcentrator has size, okay, n times lambda d of n. And this d, any fixed d, is a function that goes to infinity, as n goes to infinity. But, so this is the good news. And the bad news is that it's, unfortunately, it's very, very slowly going. So just some example, this is, there are many papers. There's a paper of Pippinger and Alon and Pudlak and Radhakrishnan and Tashma. And I'm probably forgetting some references. But just to give you a sense of what these functions look like. So lambda 2 is like log squared n over log n. Lambda 3 is log n. Lambda 4, lambda 5 is log star n. And then it becomes things that are so bad that you cannot even describe them to people. I mean, it's it's really terrible, but it goes to infinity. So okay, so we have super linear lower bounds. They are very weak, but this is what we are trying to beat. And let me talk about matrix rigidity for a second. Like one reasonable question is like, how come this model is so hard to prove? Right? It looks so. Just multiplying two matrices, it shouldn't be that hard. Well, one reason is the following phenomenon, which is again a theorem of Valiant. Is that if so I write A, by that I mean the linear transformation given by A. So if this matrix A has order n size and order log n depth linear circuit, then what Valiant shows is that, well, you can write A as a sum of R plus S, where the rank of R is at most epsilon times n, and S is n to the 1 plus delta sparse. This is true for any epsilon and any delta. I mean, you can even take like one of them to be subconstant. But not important. Let's just assume they're tiny, tiny constant, as tiny as we want them to be. And well, okay. So let's for a second. So let's say R is a long rank matrix. So you can write it. What I want to show is that this is actually a very special case of a small depth 2 circuit. And the reason is that you can write R as P times Q, where P is n times epsilon n, and Q is epsilon n times n. And then this is sparse, so your whole circuit is given by, like this would be the first layer, and then here you have some epsilon n nodes that maybe all the edges go here, and all the edges go here. And then you add some other n to the 1 plus delta edges. Let's do them in a different color. And again, they're not layered, but it's not important. Okay, so so what's the total size of this circuit, right? It can be like P and Q have at most epsilon n squared non-zero entries, and these have just a few more. In particular, for some epsilon prime, this says that A has epsilon prime n squared size circuit. Well, okay, I didn't say it. It's clear that every A has an n squared size circuit, right? Like the trivial thing would be like you can write A times I, or something like, or just A. You can do it in depth 1, in size n squared. And this shows that anything that can be computed in log n size, it's a depth reduction theorem, right? This is what it is. You can reduce it to depth 2, and the size is smaller than in the general case. Like most matrices, maybe I should have said it as well, most matrices require size n squared. This says that any n squared lower bound on depth 2 will give you a lower bound on depth log n. So these depth 2 circuits are kind of strong, you know, they're not that weak. But I also want to claim a stronger statement. So a matrix that you write like this is called rigid. I mean, if you cannot write it as a sum of low rank plus parts, it's a rigid matrix. And you know, constructing explicit rigid matrix is a old problem. And like, well, this would be one way. Maybe there are other ways. But I want to say, in some sense, if you have any hope to construct rigid matrices, you must go through, well, the problem that I just erased, through depth to lower bound, because there's this, again, this not a hard observation of Pudlak. That if A has size n to the 1 plus epsilon, depth to third circuit, then A is not rigid. So, okay, like one way to look at it is to say, well, once we have rigid matrices, we will also solve this problem. But like, at least to me, like what I think is that we should start with studying depth to circuit if we have any hope of constructing a rigid matrix, I believe. But it's still open. This is not what I want to talk about. Well, I mean, we can do something if you're willing to run not in polynomial time, but in larger running time. But I mean, I will talk about something else. So our open problem, which comes in the middle of the talk, is to prove, you know, any n to the 1 plus epsilon lower bound for depth 2 linear circuits. And as part of what I will show, I mean, I think we have a good approach for doing that. But I mean, it works in some cases, so good sign. But yeah, that's a first open problem. So let's check how I'm doing on time to decide what to talk about next. Okay, not that bad. So I will just say a few words about data structure lower bounds. Yes? I think you can even get epsilon up to a half or something like that. It depends how carefully you do it. Yes, the valiant sense, that epsilon n and, or even, yeah, let's say this sense. I mean, maybe you can get some, you can do some games with the epsilon. Okay, so let's talk about big data. So data, okay, I don't know what to say. It's a thing, right? Data structure, and they want to prove lower bound for this thing. Okay, there are many models for data structure. One model is they call it maybe I will write it. They call it a group model for some reason, even though it's I mean there's no group, it's over a field. And okay, so it's like the story, okay, there are some, it's a dynamic data structure over the group model, and the story is that you have some set of inputs, like you have n inputs, and you have a vector x that describe weights to the input, and now you have some update operation that somehow updates the weights, and now you have some query operation that you want to query the current state of the data structure. So it is given, I mean, and they're both linear algorithms. So, I mean, when you write it down, it's really like, so the data structure problem is given by A, and an efficient data structure for A is just a factorization of A into these Q and U. They are sometimes interested in slightly different parameters because they have a different story. But okay, what I will write about data structure. And then there's machine learning, which is, okay, so I really can say anything, but it comes up. There are problems like sparse dictionary learning and non-negative matrix factorization, which really, of course, they're not interested in algorithms to factor matrices, and they don't care to prove that they work. It's enough that you can, I mean, show in practice that it works, and you can approximate the matrix. So it's a completely story altogether. But even just, so I deleted my drawing of a linear circuit. Like, it looks like a neural net, right? If you've ever seen a picture of a neural net, this is what it looks like. The only difference is that you have some activation function inside the node, the computer nonlinear part. But sometimes they ignore them. So, and just, yeah. This, okay, enough machine learning. Yes, so what did I want to say next? I got caught up in machine learning. Yeah, okay. So well, as I said, we cannot prove an n to the 1 plus epsilon lower bound for the circuit. People can prove lower bounds for restricted classes of circuits. For example, if you assume that you only use, you're over the rails and you only use non-negative numbers, it's quite easy to prove like almost optimal, like n to the 2 minus the law of 1 lower bounds. If you only allow to use a coefficients of bounded magnitude, like the absolute value at most, I don't know, let's say 1, true for any constant, then you can prove such lower bounds. And we will show different cases where you can show lower bounds. And the different those cases are interesting because they sort of generalize many of the common. Okay, I mean, we all know not every matrix decomposition is the same, right? Some are worth more than others. There are common ways to factor matrices that have names, sometimes names of people, so you know they're important, like Cholesky factorization and QR and LUP and singular value and whatever, all those things. So we can put lower bounds for models that generalize some of those things. Well, you know, sometimes they are unique, and then it's not interesting like this factorization per se, but the models are more general, so it is non-trivial. So I will show you just one example in the time that I have, but first I have to do the definition. Okay, so here's the definition. So let's say C, so this is like a Pascal C, be a class of matrices. And we say H, so C is just, you know, it's a subset of F to the n by n. And H, which is another such subset, is a heating set for C. If the following happens, if for every non-zero A in C, there is some M in the subset H, such that this inner product between A, which is just the usual inner product when you think of them as vectors, so sum ij, aij, mij, is not zero. So this definition was used by Forbes and Spilka, but I will not be surprised to learn that someone came up with it before. It's a pretty natural definition. So every class of matrices has a heating set of size n squared. take H to be the class of like matrices which are 1 at one coordinate and non-zero in all others, and this is a heating set, right? If it's non-zero, this will pick out some non-zero entry. So n squared is easy, and the heating set is non-trivial if its size is less than n squared. So like n squared minus 1, or at most n squared minus 1. And the observation is that explicit non-trivial heating set for C implies an algorithm, a polynomial time algorithm for finding a matrix, let's call it B, which is not in C. It's not a hard argument. Well, you know, it's not surprising that if you can fool a class, right, you can get lower bounds. It's not news, right? It's like a dog bites a man, right? Or however this thing goes. Man bites a dog. No. Okay. No. So why is this true? Well, every element of the heating set gives you a linear constraint. So you want to find a matrix which is 0 on the heating, which is a 0 on the heating set. So every such element gives you a linear constraint. You have at most n squared minus 1 of them. So it's linear algebra, right? You find a non-zero matrix which is 0 on all the heating set, and then by definition it cannot be in C. Right? This is the usual argument, but you know it's like scaled down for the linear case. Yeah, and I just want to mention that in practice, it's not necessary, but it's often useful to consider what we call rank 1 heating set, which is just a heating set where all elements are rank 1. So here, like you have the inner product of, how do you call it, A. Like you take A inner product with X, Y transpose. It equals X transpose AY. And then you it's more similar to polynomial identity testing type problem where you think of X as variables, and you try to hit polynomials. As I said, it's not necessary, it's just something that, it comes up. Like when you actually come to design those heating sets, it's sometimes it's somehow easier to restrict yourself to that case. Okay, so is the definition clear? Good. Let me check the time. Okay, so I want to use the time I have left to prove a lower bound for some model. So, okay, so just one more definition for what is the model. Symmetric depth 2 linear circuit is just a decomposition of the form B transpose time D. So let's draw the circuit for a second. Okay, I cannot draw this correctly, but if it is symmetric, I mean, you take and you put it here, and you look at it like this, and you see your circuit, right? That's symmetric. This is over R, let's say. See, it's more natural to take the conjugate transpose and not the transpose, and then the mirror, you cannot do it, unless you have a mirror that conjugates complex numbers. So a symmetric circuit is is a very natural model if you're computing PSD matrices, right? So it's clear that every such a circuit computes a positive semi-definite matrix, and every positive semi-definite matrix has such a circuit. In fact, there are infinitely many. And we want to prove lower bound for that model, so this is what we will do. So I will prove to you actually, I can write this here. That there is explicit PSD matrix, let's call it A, such that any depth 2 symmetric circuit computed A has size, let's say, squared over 100, just to be safe. There will be a smaller constant. Most, at least. So, like, this is the optimal lower bound. Okay, let's prove it, and we'll prove it using a heating set. But it's easier if I first construct the matrix and then we will use the heating set. Yeah, I will just show you an algorithm that constructs the matrix. There are more concrete ways to do it, but I think it's easier to understand if I do it a bit more abstractly. But it will be clear that this can be done in polynomial time because there will be nothing crazy that's going on. So, okay, so here's the proof. So, okay, let's start with taking the Reed-Solomon code with length n and dimension n minus s. Let's say s will be n over 3. So the distance is, I guess, s plus 1. If you don't know what are Reed-Solomon codes, it's not that important. The only thing you need to know is that it's a linear subspace. We're over R. You usually consider them over finite field. But we are over R. It's fine. We're allowed to do it. It's a linear subspace in Rn that has dimension n minus s. And every non-zero vector in this subspace has weight s plus 1. Okay, that's the property. And it's explicit. Like, you can write a generator matrix very easily. So, yeah, it's not clear what you do after you take it. So let V1 Vs be a basis for the dual of the Reed-Solomon code. So this, the dimension is n minus s. The basis, the dual has the dimension s. And now what we're going to do, we're going to find matrix P such that, so P can be n by n, such that the following thing happen. So first of all, I want P Vi to be 0 for all I from 1 to s. And the second thing is that the rank of P is at least n over 2. So let's say, it's linear. So once you verify that there is such a matrix, you can find it using solving systems of linear equations. So this thing gives you n over 3 constraints. So you have 2n over 3 more dimensions to work with, and you just want, P should have a rank which is fairly large. So this is easy to do. Sorry? I'm constructing a matrix that will be hard. I'm constructing a matrix, and we prove that it's hard. And the construction is over. Now you just let A be P transpose times P. This is the matrix I want, and you can do it in polynomial time. Okay, so now let's claim that A has a lower bound. First of all, okay, so we said A is clearly positive semi-definite and A is explicit. So we just need to prove the lower bound. Okay, so yes, let's suppose you can also write A as B transpose times B for B which has sparsity less than, what did I say, right, 100. For B which has very small sparsity. Okay, so here's the thing, the rank of A, let's put it, I mean, it's also, it equals the rank of P, right? It's also at least n over 2. So when you do this to decomposition to B and B transpose, this is n and this is m, and this is m and this is n. What I want to say is this m better be at least n over 2, right? Otherwise, it cannot be the case, because the rank will be too small. So m has to be somewhat large. And now the point is, if you have here at least n over 2 rows, and the sparsity is so small, there has to be one row which would be somewhat sparse, and also non-zero. Let's just imagine that in the previous sentence it says non-zero rows and not rows, because it's the same. I mean, if you have zero, you can just remove them and get a smaller decomposition. So let's assume B has non-zero rows, and what I want to say is that because the sparsity is small, the total sparsity is small, and the number of rows is large, just by averaging arguments, you need to have some row which would have at most, I don't know, n over 10 non-zero elements, right? That's clear. But now what I claim is that this implies that there must exist an I from 1 to S such that B of Vi is not 0. Why is that? And VIs are those kind of things. And why is that? Because, well, I mean, you know, if this is 0, this means that this row is orthogonal to all the dual elements of the Reed-Solomon code. So this thing must be in the Reed-Solomon code. But it cannot be, right? Its weight is just too small. It's n over 10. It's non-zero, and it's n over 10, which is smaller than n over 3. Right? Is that... Well, this is a clear statement, but like the rest of the thing, I hope it's OK. So what we have now, my claim is, so now we have, if we look at VI transpose, B transpose, B, VI, right? This would be R, this would be the norm of BVI squared. This will be greater than 0. But what happens if we plug it to P? Well, now you just have VI transpose, P transpose, P, VI. This equals A. But this is 0, right? We picked P, so that this thing is always 0. So this equals 0. So there cannot be an equality, right? That's the end of the proof. I hope it was not too technical. I liked it, but well, the important thing is that I enjoy, right? So let me just probably have a few more minutes left, right? Or am I? Yeah, OK, good. So I will just mention some open problems. Well, there was that thing that was written somewhere here about proving better lower bounds for depth 2 circuits. That's certainly open for general depth 2 circuits. One thing which I think this, like a natural question which follows from this proof is that, okay, now is it the case that, maybe I will first say it in words. Is it true that, let's say we only want to compute PSD matrices, is it true that you can convert any depth 2 circuit to a symmetric depth 2 circuit, and have a small blow up in size. Right? This is okay, I will write it that size S depth to circuit for PSD A implies size, I don't know, let's write it as S to the 1 plus epsilon symmetric. Depth to circuit for A. If it is the case, then we will have a lower bound, right? If you can prove this, we will get a lower bound for general depth to circuits because we can prove lower bounds for symmetric circuits. Of course, I mean, like, the smaller the epsilon, the better the lower bound is. Yeah, particularly good reason to believe this should be true, but it will also be good to know it's not true. I mean, yeah, it's written 50-50 on that conjecture. So that is one thing. I didn't think about it, and if I try to think about it now, I will probably be wrong. So let's think about it later. No, I mean, so it has to be at least n. I mean, it's at most n squared, and it has to be at least n squared over some constant. So up to the constants, yes. Yeah, so this is one thing. The second thing is that to find more uses for this technique in particular, it's good. I mean, we are interested in can you construct rigid matrices using heating sets. By that I mean, okay, so I mean, we know the answer is yes, but unfortunately the matrices we get are the same parameters we can prove without heating sets. So like in some sense you can, but what is going on here? Yeah, but it's interesting whether we can get improved parameters, like maybe not even getting to the parameters that Valiant need, but just to get some improvement over the current weak rigid matrices we can construct. And one reason I think this is interesting is that there have been several works recently, several papers that prove that certain matrices that we would have hoped to be rigid, that have certain symmetries under some group operations are not rigid. Things like Hadamard matrix or Toeplitz matrices and circulant matrices, they are not rigid enough for the Valiant parameters. And you know, if you just find something that is 0 over some heating set, there's no reason to assume it will have any of these symmetries. So I think, I mean, this might, well, at least to me, it looks like something that can bypass these obstacles that we have using matrices that have a lot of symmetries that are natural to describe, but are not rigid enough. Okay, I think that's all of my questions.